All right, good morning. Looks like we didn't get out of the term before winter hit, unfortunately. Good on you to make it this morning. I hope to finish our last material today, so I'm going to get started right away so that we can do something else on Wednesday. So we are in the midst of pipelining, so we're going to finish pipelining today for sure, and then talk about a concept called superscalar, which shouldn't take very long at all, and then we'll be done. So pipelining, as you will recall, we have these 5 stages in hardware that correspond to the 5 steps of instruction execution. And ideally, we would like to fetch or start a new equation in every clock cycle and finish an instruction. Did I say equation? Start an instruction in every clock cycle and finish an instruction in every clock cycle to get maximum throughput. But we've seen that there are some things that can happen that will stall the pipeline, right? And one of them is what we call a data hazard, where a particular instruction requires a value in a register that was calculated in a previous instruction, and if that previous instruction hasn't gone all the way through the pipeline yet, that new value is not in that register yet, so a subsequent instruction that requires that value has to wait. It's got to wait until that new value has been written back into that register, then it can go read it out of the register and do its thing with that number. And we saw that we can do something called operand forwarding in order to get around that. We also talked about pipeline stalls due to memory accesses. Typically, if the thing we're looking for in memory is actually in the cache, well, then it can be read out of cache very quickly in one cycle in step 4 of the instruction execution, and there's no stall in the pipeline. But if there's a cache miss and we got to go to main memory, that takes a whole lot longer, and now the pipeline is stalled in that particular step. And of course, if one instruction is stalled, then all subsequent instructions are also stalled, right? They all have to stop wherever they were at the time. And so we talked about how we have that because of memory misses. The third thing we started looking at is, what about branch instructions? And we talked about first unconditional branches, which means that that branch instruction is executed every time. It's not conditional on everything. And we saw that in a case like that, and here's a typical diagram for a pipeline where we have multiple instructions, right? And we're fetching one instruction after another. And if the first instruction is an unconditional branch, well, where we're branching to is not calculated typically until the 3rd step of that instruction execution, the compute step, right? That's where the branch target address is computed. And therefore, in the meantime, we fetch the next 2 instructions that come after the branch, okay? And it's not until this point in time here at the end of stage 3 where we now know where we're branching to, and then the processor will go there and it'll fetch that new instruction. In the meantime, these 2 have to be discarded, right? Because they come right after this branch instruction in your program flow, but logically the processor shouldn't have gone there. It should have gone to some instruction somewhere else in memory, but the address of that memory location isn't computed until this point in time. In the meantime, the processor has fetched these next 2 instructions, which it turns out shouldn't be executed, so they have to get discarded, and we have what we call a branch penalty. 2 cycles of the clock in that case. And then we talked about how, well, the way we can reduce this branch penalty is instead of computing the address where we're branching to in step 3 of the branch instruction, let's move it into step 2, where we decode the instruction, we see it's a branch instruction, and right away we calculate the target address. We don't wait until step 3. So that, of course, requires some additional hardware in stage 2 of the processor in order to calculate that target offset, and then I have right here. So in stage 2 now, we actually calculate the address of where we're branching to. So in the meantime, we have fetched the next instruction, which will have to be discarded, but then at this point in time, we know where we're branching to instead of at this point in time, so then we can go to our proper address. So now the branch penalty has been reduced to 1. Okay, so we move some hardware, or we add hardware to stage 2 of the processor to calculate the target offset sooner in step 3, in step 2 rather than step 3. And the same as this. So in stage 2 of the branch, we calculate where we're branching to, and if it's a conditional branch statement, we also check whether that condition is true. Okay, those 2 computations are done in stage 2. So then we know at this point in time, we know where we're branching, we know if we're branching, and we know where we're branching to. Okay, so in the meantime, we fetch the next instruction, it'll have to be discarded, and then we can branch to the correct instruction. So we still have a branch penalty of 1 clock cycle. Okay, even with this slot here for this instruction, which comes right after this branch instruction, it still gets fetched. Okay, if the branch doesn't happen, for instance, if it's a conditional branch and the branch condition is false, meaning don't branch, well, that's fine. Then this instruction needs to be executed. We started it, we finish it. Okay, but if the condition is false, or if it's an unconditional branch, which means always branch, well, then you fetch this instruction. Now it's got to be discarded because it's not supposed to be executed because we're supposed to branch instead. Okay, so we call this the branch delay slot because we still have this branch penalty of 1 clock cycle. So what do we do? There's 5 steps, right? Fetch the instruction and update the program counter to point to the next instruction. Not the one you're branching to, the next instruction that follows. Decode and read registers, compute. So without any of this fancy stuff, that's where the target address would be computed, right? Now where does that target address have to end up in for the processor to actually go to that address? What register? What register holds the address of the next instruction to be executed? Program counter. I've said that a million times, right? So in a branch instruction, the address you're branching to is calculated here in the compute stage, right? Next stage is memory. Well, there's no memory read and write, so nothing happens. But this is the write to register stage. Any results get written to registers here. So the new address you're branching to is computed here. It's here where it's going to actually be loaded into the program counter, so that now you know where to go, right? So it's got to finish. We talked about, well, what about conditional branches? Because in a conditional branch instruction, 2 things have to be computed. You have to compute where you're branching to, right, and typically what that computation is adding the current address in the program counter to some offset in the instruction, in the branch instruction. But in a conditional branch, we also have to do some sort of comparison. Are 2 values equal? Is one greater than the other, etc.? Okay, that's a computational task as well, which is typically done in step 3 of the instruction execution or in stage 3 of the data flow. So we said, well, okay, what are we going to do that? Well, let's take the same approach as the target address computation. Let's add hardware to step 2, or to stage 2, the decode stage, in order to not only calculate where we're branching to, but also whether we're branching, if this condition is true or not. Okay, so we add in comparator to stage 2 of the hardware. So again, we have to add hardware, and we add it sooner in the process so we can make these branch decisions sooner, and so we don't have such a big branch penalty. Okay, so that again, you still have though this 1 cycle delay. It's exactly no branches moving the hardware forward to that. What happens? Okay, that means we've got what we call a branch delay slot. This, what can we do with that? Well, what we can do with that is we can move an instruction, because that instruction right after the branch is going to be fetched, regardless of whether we branch or not. It's going to be fetched. That instruction will be started. We say, okay, well, if we start the instruction, let's put an instruction there that we want to execute every time, even if it is a branch. Okay, so yeah.
Before you go on,
Yep.
does this imply that some compilers are more intelligent than others?
I would imagine, yep, because not all compilers are the same. Yep.
You'd want to choose one that does.
Yeah, so compilers are software, right? They're a program written by somebody, and so there's intelligence in there. Some compilers will be simple, and I imagine wouldn't do this. Others would. Yeah.
You have 5 things running simultaneously, right? I'm just trying to picture what would happen when you actually hit the branch instruction. I can't remember. Would it cut off everything that's running before it? If that makes sense. Like
No, no. Every instruction before it would finish executing.
Okay.
Yep. Because in a branch instruction, so branch delay slot. Either you take an instruction from above and you stick it in there, or you put a no-op in there, or you could just leave that instruction in there. And again, this is the compiler, whoever writes the compiler, right? These are techniques in software to deal with this. Or you could just leave whatever instruction is there and there, recognizing that sometimes it's going to be started and have to be discarded because we're actually branching. If we go forward here, so here we've got some instructions, okay? We've got an add instruction, and then we have a conditional branch instruction. And then we've got instructions that come after that, okay? And where we're branching to, if this is true, is down here at target, this address, okay? So we go along, we do this, we check if the contents of R3 is equal to 0. If it is, we want to branch down to there. We don't want to do any of these. If this is not equal to 0, if this is false, well then we keep going with these instructions, obviously, okay? Now, because of this branch delay slot, we've got this one cycle branch penalty, meaning that when we execute when we get to here, in the second cycle or the second step of this instruction, we're going to fetch this instruction because we don't know yet if we're branching and we don't know where we're branching to yet, okay? So this instruction will be fetched. So the idea is, okay, we're going to fetch it regardless. Let's put an instruction there that we want to finish, whether we branch or not. So in a case like this, you'll see that this add instruction up here has really nothing to do with this instruction here, right? This one is adding R8 to R9, putting it in R7. This one is checking the contents of R3, okay? When this program was written, the programmer obviously wants this instruction to be done, regardless of whether we're branching or not, right? It comes before the branch instruction. So, given the fact that this instruction will be fetched, regardless of whether we're branching or not, why not put this instruction down here and let it fetch and execute, okay? Now what we've done is we've filled this branch delay slot with an instruction that we want to execute whether the branch executes or not. So now we have this here. Okay, so we hit this branch, okay, we fetch it, we start decoding in step 2, we figure out whether this is true or not, and we calculate this target address. During step 2 of this instruction is going to be fetched. Okay, so it's the next instruction that gets executed. Even if we're going to branch, this isn't going to happen until this instruction has finished executing, and then we branch to here, and now we don't have any branch penalty at all. Okay, now obviously you can only do this if this, if this instruction does not require the result of this instruction, right? If this instruction actually, if this is R8 added to R9 put into R3, well then obviously it has to be executed before the branch because the branch is requiring R3. Okay, so in that case you can't put it down here. Okay? Was there a question over here?
You answered it.
I answered it. Okay, great. Yeah.
And this is something that would be done by the compiler.
This would be done by the compiler. The programmer is going to do this because you're thinking, well, I'm doing things in this order. The compiler is going to look at this and go, oh, conditional branch delay slot. Can I take an instruction from above, which is not logically related to this one, and slip it in here? Because I know it's going to get executed regardless of whether we branch or not. And if I can do that, then I'm not wasting that branch delay slot. okay? I'm not fetching an instruction that I will then have to discard if I actually branch. If the compiler can't do that, it's just gonna put a no-op in there, a no-op instruction, which does nothing, okay? Because it knows that it could potentially get discarded. Or I guess it could just leave this instruction in here, because, you know, sometimes this condition will be false and we won't branch, so we do want this one to go here, okay? Okay, so that's branch delay slot. So can we do anything else? Well, yes, we can do something more, because there's still the chance that even with all of everything we've looked at so far, that we still might waste one clock cycle by either fetching an instruction that we have to discard, or there's no other instruction before the branch instruction that we can slip into that slot, or we have to put a no-op in there. So there's still the possibility of a branch penalty. So computer engineers have said, okay, well, is there anything else we can do? And they said, well, when do we actually make a decision on what the next instruction to be fetched is? It's actually in step one, right? Because what happens when you execute one instruction, step one in that instruction is fetch the instruction and update the program counter, right? To point to the next instruction. So really in step one already, in a sense, the processor's made a decision of where it's going to next. It's going to the next instruction by updating the program counter to point to the next instruction that comes after the branch, right? So they said, well, in step one, what if we can predict, first of all, two things. Can we anticipate that the instruction we're fetching in step one is actually a branch instruction? And if it is, can we actually predict whether we're going to branch or not? Because if we can, well then, instead of updating the program counter to point to the next instruction that comes right after the branch instruction in the program, if in step one we can already see that it's a branch instruction and we can predict whether it's going to happen or not, well then just update the program counter to point to the address of the instruction you're branching to. And now we have no branch penalty at all, because you're doing everything in step one of the branch instruction. You're anticipating that it is a branch instruction, and you're predicting whether it's going to happen or not. And if you're right, that if your prediction is right, there's no branch penalty, because now you've updated the program counter not just to point to the next instruction right after the branch, but you've updated the program counter to point to the address of where that branch goes to. Okay, so now possibly we can get rid of the branch delay slot entirely. There's no branch penalty. Okay, so in step one, because typically when do we figure out what an instruction is? It's in step two where we decode the instruction, right? So now again, it's the same strategy. They're pushing things forward, back in time, I guess, right? Earlier, right? Instead of waiting until step two to decode and figure out this as a branch instruction, we're going to do it in step one, okay? If it worked going from 3 to 2, let's do it from 2 to 1 and get rid of the branch delay entirely, okay? So we can further reduce the branch penalty with branch prediction in the first step of the 5 steps to guess whether or not a branch is taken, right? If we predict correctly, great. In step 1, it's a branch, we predict whether it's going to happen. Yep, it's going to happen. Or we think it's going to happen, so we update the program counter right away in step 1, not to point to the next instruction, but to point to the instruction we're branching to. Next clock cycle, that's where we go to fetch that next instruction of where we're branching to. No branch penalty, okay? Of course, if we're wrong, well then we still incur a branch penalty, okay? Well, how do we do this, right? Well, we use what's called a branch target buffer. So there's going to be a small, fast memory on the processor which is going to hold information about all the branch instructions in our program. And that's what the processor is going to use in step 1 of the branch instruction to figure out, first of all, is this a branch instruction? And should I take it or not? Should I take the branch or not? Okay? What's my prediction of whether this branch will be taken or not? So what do we need to do that? Well, you write a program, there's going to be a number of branch statements in there. That program gets compiled, those branch statements will be at certain addresses in memory, right? That's part of what the compiler does. It figures out using your directives. You might tell it where to put it in memory, and then it'll know, the compiler will know all of these addresses of all these branch statements, okay? So all you have to do is put these addresses in this little table, and every time you fetch an instruction, you look at the address of that instruction, you look in this table, you go, oh, this is a branch instruction. I don't even have to look at the bits in the instruction itself to know it's a branch instruction. This little table over here tells me that, oh, instruction at 0x100, that's a branch instruction. So I know, even just from the address of the instruction itself, that this is a branch instruction. So in step one, when I fetch this instruction, I'm fetching from a particular address. I just compare that address to all the addresses in this table. If it's there, oh, I know it's a branch instruction, okay? So that's part one. I know that in step one, I know I'm dealing with a branch instruction. The other thing we're gonna have in this table is 1 or 2 bits that are gonna tell the processor whether it should predict whether this branch will be taken or not. And we're gonna talk about how that works in a second. Okay, so you just have this little bit of memory. You fetch it, every instruction you fetch, you compare the address of that instruction, where it's stored in memory, to the addresses in, oh, no, it's not in this, it's not a branch. Okay, well then I just keep going, step 2, decode and do the rest of the thing I need to do for that instruction. But if the instruction that I fetch at this address is in my little table here, this branch target buffer, well, the only addresses I have in this branch target buffer are the addresses of branch instructions. So if the address of the instruction I'm fetching is in this table, I know right away it's a branch instruction. I don't have to decode it right away. Right away in step one, I know it's a branch instruction. Great. Then I'm gonna look at these other bits to say, oh yeah, for this instruction, I should predict that it's gonna be taken, the branch will be taken or not taken. Okay, so how, there's no real computations here, right? These are concepts. And so you just have, you either understand what's going on or you don't. So, in terms of what I could ask you, well, what's static prediction versus dynamic prediction, right? How does one work versus the other? Show me an example, right? You do that. A couple of different ways, static and dynamic. Static just means the processor will predict the same way every time, okay? And so you can think of, for instance, loops. We got lots of loops in programs, right? So don't think of assembly, think maybe of C, where, we have while loops and we have do while loops, right? Where's the condition on a while loop? It's at the start of the loop, right? While this condition is true, do this stuff, right? Where's the condition for a do while? It's at the end of the loop, right? Do this while this is true. If it's still true, go back, do it again. So for some loops, we might want to branch at the top, right? A while loop. If the condition's false, you're going to branch. You're going to skip the loop and keep going with what comes after it. Do while, if the condition's true, what are you going to do? You're going to branch, go back up here, do the loop again, okay? So if your branch statement is at the top, how often do we write a while loop that you never go into the while loop? Usually not, right? Usually you go into and you do the loop at least once, right? Maybe the second time you go to the while loop, you go to the top. Okay, now I don't do it again, but usually the first time. So if your branch is at the top of a loop, it probably makes sense to predict that it will not be taken, right? If it's a while loop, you're going to want to go through the while loop. Typically, you write your program so you go through the loop at least once, right? So that means that branch statement at the top of that while loop, you're probably going to predict, no, I'm not going to take it. I don't want to skip the loop. I usually go through the loop at least once, right? So you're going to predict not taken, which means go into the loop, do it, right? Go back up to the top of the loop. Usually you go through a loop more than once. You go through a loop a number of times. So if you predict not taken for the branch at the top, you're going to be right, because typically you do go through the loop. Finally, you're going to get to the end where the condition is false. You're still going to predict for static prediction. You're still going to predict don't branch, right? Go through the loop again, but now the condition's false and you're wrong. Okay, well now you got a penalty, right? You are going to branch. Your prediction is wrong, so there's going to be a branch penalty. But every time you go through the loop, you're going to predict right, because you're predicting, no, don't branch out of the loop, go through the loop again. Okay, the opposite is true if you're branching at the bottom. like a do-while loop, right? You go through the loop, you check the condition. If it's true, what do? You branch back to the top of the loop and do the loop again, right? So in this case, you're going to want to branch. You're going to, for a branch instruction at the end of a loop, you're going to want to predict, yes, branch, right? Because you're going to go back and do the loop again. At some point, you reach the bottom of the loop and the condition is false now, so you're not going to branch. Well, you still predict branch, because in a static case, you predict the same way every time. And so, okay, you're going to be wrong that last time, okay? So that's the static prediction. You predict the same way every time, but again, the compiler can be intelligent about whether it predicts whether a particular branch should be predicted as being taken or not taken, depending on where the branch is in the loop. If the branch is at the top of the loop, it's better, you're going to be right most of the time if you predict don't branch. If the branch is at the bottom of the loop, you're going to be right most of the time if you predict yes, branch back to the top of the loop. Okay, so the compiler can be intelligent about that. And how does it know? Well, it can look at the offset in that branch instruction. With the compiler can look at the offset, right? Again, how is the branch address calculated? The processor takes the address of the next instruction to be executed and adds an offset to that. If it's branching backwards, like back to the top of the loop, you add a negative offset to go to a lower address. If you're branching forward, you add a positive offset to go to a higher address. So the compiler can just look at the sign of that offset. It knows whether that branch is going forward or backwards, and then it can adjust whether that branch should be taken or should be predicted as taken or not taken. Okay, so again, in general, though, static means predict the same way every time. If you predict, somewhat intelligently, you're going to be right more than 50%. If it's just random, well, the accuracy is maybe going to be around 50%. Okay, when you predict wrong, you still have a branch penalty. You lose a clock cycle, right? You fetch an instruction that you have to discard. Okay, but when you predict correctly, you don't. So that's. So I'm going to talk about the final exam a little bit more at the end, I hope. And obviously on Wednesday, if not today. Dynamic says, well, we can do a little bit better than that, okay? Think again of our branch statements at the top of the loop and at the bottom of the loop. Say, take the one at the bottom of the loop, like a do-while loop, okay? You're going to want to predict, yes, branch, because we're typically going to go back and do the loop a number of times, okay? Now, when if you predict yes, branch, you're going to be right the first time, the second time, the third time, until the last time through the loop. Then you're going to be wrong, okay? So in the static case, or in dynamic, we say, okay, well, we predicted branch. When we get to the last case, we found out actually we were wrong in our prediction. We have to not branch. We have to drop out of the loop and keep going. Well, let's keep a bit somewhere, and let's change the prediction. Okay, we were predicting branch, then finally we didn't branch. Okay, well from then on, let's predict, this time we didn't branch, let's predict not branching the next time we hit that instruction, right? Because again, usually, when things happen one way, they're usually going to happen the same way the next time. Not always, but usually, okay? So dynamic says we're going to keep some memory somewhere, a bit somewhere in memory, and we're going to keep track of whether a branch actually executed or not. Okay, if it actually executed, well, that means the next time, let's predict, yes, we branched. If it didn't branch, well, then the next time we hit that instruction, let's predict, don't branch, because that's what happened last time. And typically, things happen the same way a number of times. Okay, so that's what we call dynamic branch. So we basically have a two-state machine for every branch instruction. Either we're in the state where we're going to predict branch, or we're going to be in the state where we don't predict branch. Okay? And we have a little, this is all very consistent. Forget about this one at the bottom for now. Okay, we've got a simple one-bit history. So we've got two states. Likely take the branch, likely not take the branch. Okay? So if we're in a loop and this branch is at the bottom of the loop and we keep branching, we're going to be in this likely take state. And every time we branch, right? Every time that branch is executed, branch taken, yep, we stay in the same state so that the next time we predict, yes, take the branch, likely taken. At some point in time, we're going to be wrong, and the branch isn't taken. So that branch not taken moves us to this other state, which is now predict likely not taken. Okay, which means the next time we hit that branch, we're going to predict likely not taken. If we're correct, and branch is actually not taken, then we stay in that state. As long as we're correct in our prediction, we stay in that state. At some point we're wrong, moves us to the other state, so that the next time we predict the other way, okay? Well, this helps a little bit. It moves us, it's not like static where you always predict the same way for that branch statement. Our prediction can change based on what happened in the past, okay? But again, think about what happens in a loop. Even if I have this simple 1-bit dynamic branch prediction, that branch instruction at the bottom of a loop, yes, branch, yes, branch, yes, branch, yes, branch. At some point, I'm going to drop out of the loop, which means my prediction's wrong. And I'm going to move over branch not taken. I'm moving over into this state, okay? Keep going with the instructions after that loop. Often loops are inside bigger loops. At some point, I'm probably going to come branch way back up here, and I'm going to hit this same loop again, right? And then I'm going to hit that same branch instruction at the bottom of that inner loop again. Now I'm over here, likely not taken. But of course, the first time through my do while, I'm probably going to go back up here. I should take the branch. So I'm going to be wrong, okay? So we can make this even more intelligent by making it a, how do I get rid of this thing now? There we go. A little bit more complex, a 2-bit history. Okay, and by the way, this 1 bit and 2 bits are in that table that I was talking about before, which holds the addresses of all the branch instructions. There's also going to be a bit or 2 bits, which tell the processor whether it's going to predict taken or not taken. Okay, and those are the bits we're talking about here. So it's a little bit, now we've got a 4-state machine. So now we've got 2 states where we're going to predict, yes, take the branch, likely taken or strongly taken. Okay, in both, if we're in either one of these, we're going to take the branch. We're going to predict take the branch, I should say. These two, we're going to predict don't take the branch. Okay, likely not taken, strongly not taken. In both of these, we predict don't branch. Okay, again, if I'm in any one of these states, if I'm in this state, strongly not taken, I'm going to predict don't branch. If that's actually what happens, so I moved. Branch not taken, I stay there. As long as I'm correct, I stay in this state, okay? At some point, I might be incorrect. And the branch was not taken, which is going to take me over here, which says likely not taken. Okay, the branch was taken. It doesn't move me to a state where I'm next going to predict take the branch. I'm going to stay in a state where I don't predict. So now I have to be wrong twice in order to actually change from my prediction of don't take the branch to my prediction of take the branch. Okay, so that eliminates this, this penalty I get at the bottom of this loop. I get to the bottom of the loop, I don't branch, I'm wrong, right? I come back, eventually I'm going to come back to that loop through some bigger loop, some outer loop, right? I'm going to hit that branch statement again, I'm over here now. I didn't move down to here because I was wrong, I moved over to here. So I'm still going to predict, I should have been the other way. I'm taking the branch at the bottom. So branch at the bottom of the loop, I predict take the branch, right? Keeps doing this. Oh, I can't do this opposite ways. Okay, keep branching. I keep staying in this state. Finally, I get to the end of that loop. The branch is no longer happening. Moves me over to here. Okay? I keep going because I'm out of the loop now. At some point, I loop back and I hit this inner loop again. I'm over here. I hit this branch statement. What do I predict? Take the branch, which means, and that's what I want to do because typically you go back to the top of a loop. So I'm not wrong this time. Okay? So it moves me back over here. I have to be wrong twice before it moves me back to the other prediction. Okay? So this has been shown to be a little bit more accurate. based on how branch instructions typically work in loops, okay? Or how loops typically execute. So that's what we call dynamic branch prediction. All right, any questions about that? Yes, sir.
Would dynamic for the first prediction work the same as static?
What do you mean by the first?
Like-
Well, yeah, you gotta start somewhere.
Yeah,
Yeah. So there again, you know, if the branch is at the bottom of a loop,
yeah,
you're probably gonna set it up, the compiler would probably set up the state to be branch, predict the branch, right? But it could be wrong at the start. Okay, so that, you know, I know, what's the advantage of, I'm just thinking of possible questions, right? What's the advantage of a 2-bit history over a 1-bit history? Right? That's the kind of stuff that I could ask you. Yes, sir?
Is there any disadvantage with the 2-bit versus a 1-bit? Like, is it more computational power somewhere? Or...
Well, I'm sure there's gonna be instances in programming, like for instance, if you, no, what I was about to say isn't right.
In very few cases, maybe it's better to have 1-bit because of the way the code is written.
Yeah, I mean, depending on how the code is written, it could be that you only ever, if you're wrong once, you do wanna change, because the next time it's likely to be that way, but
Yeah.
yeah. I mean, it's, you know, 2 bits of memory versus 1 bit of memory, that's not really a disadvantage. Yeah, but most of the time, this is gonna be advantageous. Yeah.
Question that comes to my mind is, how much of this happens in the processor as opposed to in the compiler? Because how do we ensure that the program is compatible at various levels of computer?
Yeah, good question. Most of these techniques, if not all of them, are done by all computers these days, right? Very few of them won't have this. So there has to be, you're right, there has to be some sort of standardization, because the compiler is the one that is looking at these instructions and could start the prediction by what it writes in that buffer table, or maybe it doesn't have to, right? It could just be that the processor does it once the program starts executing. The first time it hits that branch instruction, maybe it doesn't know what state it should be in. It just picks one by default. And then, you know, if it's right, great. If it's wrong, yeah, you got a penalty that first time, right? So that's a good question. I don't know the full details of that.
I'm kind of thinking back, way back, when I first started running AutoCAD, we had to buy a separate coprocessor to even run it in a 286.
Right, because it had to be compatible with the software
Yeah. And so
or
I'm
the
thinking
compiler.
that, you know, if you come up with these advanced things, how do we ensure it's gonna work on all the computers that we expect it to
Yeah,
run on?
yeah, good question. I don't know the full answer.
I can't remember, I think we talked about this at the end of class last time, but putting all of these things, like, this little memory, you've got a computation, you've got a comparator, all in like step 2, isn't that just delaying your clock cycles, making it not efficient anymore? Like, your whole point is to eliminate the delay between clock cycles. By putting this all there, you're essentially extending that clock cycle. Which
Well,
is
not necessarily,
anything.
because you can just have more hardware doing things in parallel,
Okay,
right?
okay.
Okay, yeah, I'm sorry I don't have all the answers. I mean, we're not getting into the details, we're just looking at some of these techniques. Okay, so that's the end of pipelining, unless there's any other instructions. Questions? I've said the word instruction about 1,000,000 times in this course. What we mean by branch prediction. So that's it for pipelining. Okay, so data hazards, memory read writes, both of those can stall the pipeline. And then with branches, we've got this branch delay slot that causes us, and branch penalties. And we looked at a number of different ways that we can try to mitigate those delays. Okay? Okay, well, let's look at the very last topic then, which is pretty short, called superscalar operation, because again, there's a lot of stuff, a lot of optimizations that have been done to computers that we don't have time to look at, but this is sort of the next one in the evolution. Superscalar. So we've got this 5-stage pipeline. We fetch one instruction at a time, right? And we've got stage 2 of the stage 1, 2, 3, 4, 5 of the hardware. All those stages can only handle one instruction at a time. It's like an assembly line, you've got 5 stages, you've got one instruction in stage 1, and then, you've got one instruction in stage 5, you've got the next instruction in stage 4, the instruction after that in 3, 2, 1, okay, but you got one pipeline. So, somebody in the past said, well, why don't we have multiple paths through the factory? Instead of one assembly line that every instruction has to go through one at a time, or one behind the other, what if we have parallel paths through the assembly line? Okay, so in our car manufacturing example, instead of having only one station that drops the engine in, what if we have 2 stations that drop the engine in? So they can both be dropping an engine in a different automobile at the same time. Obviously, we're going to increase throughput, okay? So the same kind of concept here. We're going to have, we're going to enable multiple instruction issue such that we can process more than one instruction per cycle, okay? It's called a superscalar processor. So and I'll show you a block diagram in a second. It has a fetch unit, which instead of fetching one instruction at a time, it'll fetch more than one instruction at a time. So instead of fetching one instruction at a time through our program, it'll take 2 at a time, or maybe 3 or 4 at a time, okay? And then we're going to have a dispatch unit, which we haven't really had so far. We haven't had the need for it, which is then going to take these instructions and put them in an instruction queue in some order, such as to optimize the pipeline, okay? And then we've got a completion unit, which writes results to registers. So we're doing the same kind of stuff, but we've got sort of these bigger blocks that are a little bit more sophisticated, okay? And again, we're not going to look at the nitty-gritty details of how it's done inside. We're just getting an overview of what's going to happen. So this is what it looks like, okay? So here we've got a fetch unit. So this is the hardware that is responsible for going to memory and getting instructions from memory, okay? And in the past, we only got one instruction at a time. Now we're going to get more than one instruction at a time. It might take them, it takes them in bunches, okay? It's going to look at these, and there's intelligence in here. It's going to look at these, and it's going to put them in a particular order into the instruction queue, okay? And so this is going to be sort of a buffer. It's a queue, it's a lineup of instructions, and then these instructions are going to be going 2 at a time or more, but at least 2 at a time. We'll be going to a dispatch unit, and dispatch unit looks at these 2 instructions and says, okay, I know what these 2 are. I can send them on 2 different paths through my assembly line, through my pipeline, okay? Typically, most of our instructions are of 2 basic types. Either we're computing something, like we're adding 2 numbers together, subtracting 2 numbers, instructions like that, or we're going to memory to either read and write. Now, read and write instructions also require a computation, right? You got to calculate the address in memory that you're going to. But this has to do with memory. This has to do with just crunching a couple of numbers, okay? 2 different things. So we're going to have 2 different paths through here, 2 different stages. So, these 2 instructions that come in here, the dispatch unit looks at them and goes, oh, one's an add instruction. I'm going to send that one here. The other one's a store instruction. I'm going to send that one here. Okay, 2 different instructions require 2 different types of processing. We'll send them in parallel through these 2 parallel paths. Okay. Again, these are interstage buffers, right? So this is one clock cycle is processing 2 instructions now. Okay, those will then go to another block, which is going to write the results of that either to memory or the results of the add instruction to another register. Okay, so that's basically what's going on in a superscalar. You still have just one program. You still have just one program counter that's going through your program. But instead of fetching instructions 1 at a time, putting them into the pipeline 1 at a time, we're going to fetch multiple of that at a time, and we're going to put them in parallel through here. Yeah?
And they can, I'm assuming these instructions can never be the same type, so both of them.
Right. If I got 2 add instructions, one right after another, well then I can't put one here and here, right? the second add instruction has to wait for the first add instruction.
So, does it always just fetch pairs that it can simultaneously run? So-
Well, 2 or 3, but part of what the, now where does it happen? Does it happen, it wouldn't happen in the fetch unit. It's either in the instruction queue or the dispatch unit. Oh, I forget where it happens now. Something in here is gonna look at these instructions and go, oh, I've got 2 add instructions, one right after another. I know if I put those, if I dispatch those both at the same time, one has to wait for the other, which is not optimal. So instead, well, can I put some other instruction between them, like a load instruction? If I can do that, then the first add instruction goes here and the load instruction goes there. And then in the next clock cycle, the second add instruction goes there. So I'm not, you don't want anybody lazy, not lazy, you don't want anybody sitting around doing nothing on the assembly line. Every clock cycle, you want to put an instruction in both of these. So there has to be some intelligence here that can maybe rearrange some of these instructions so that I don't send 2 add instructions here at the same time. If there's 2 add instructions in here, one after the other, maybe I want one to wait a little bit longer, and I take a load instruction and put it in there instead. Does that make sense?
Just my next question. So, in the, would there ever be a possibility that one of like pieces of the circuitry sends 2 of the same instructions that causes like a clock cycle penalty?
Yeah, I'm sure there is. I mean, there's going to be cases where the dependencies of the instructions will not allow you to, you know, if I got 2 add instructions, one after the other, and I don't know, maybe I got a load instruction like that, right? So there's probably cases where I can't, store would be better. There's probably cases where I can't take the store and put it up there, right? In which case, that would be good, because then this add and this store, the add goes through here, the store goes through during the same clock cycle, great, right? But if this store is actually storing the result of that add instruction, well then I can't put it before it, right? That logically it wouldn't work. So in a case like that, yeah, there's probably going to be some cases where you don't have an instruction going through here, right? Okay, so that's basically how execution units here. Of course, if we want to get really complex with the hardware, we could have multiple ones, right? Meaning 2-stage here, load store, we have to calculate the memory address that we're writing to or reading from, and then we have to go there and get it. That's the 2 stages that have to happen here. This is just 1 stage. Add the 2 numbers together, right? This is 2 stages. Calculate the memory address. Second step, go and get that, whatever's at that memory address. That's, you know, it's possible that we could have multiple outputs here. We're not just generating one result here. This could be generating a second result, which we have to write somewhere. So now these, that's done by this here, okay, are done by this. So that's why this is a 1 stage and this is a 2 stage, okay. Scalar works. Minimum superscalar arrangement consists of a load store unit and an arithmetic unit. So 2 of these, because of index mode address calculation, load store unit has a 2-stage pipeline. It's referring to here and here. Yeah, whatever. Of course, now register files would have to have more than 1 input because we've got multiple things coming in. That's all this is saying. Stage, no big deal. So, for instance, if we've got an add, load, subtract, store, okay? These are 4 instructions that are going to be going through, coming out of the queue into our superscalar. This is an add instruction, so there is no memory step required for an add instruction. We're not writing or reading memory, okay? So we can get away with only 4 steps for an instruction like that. And this is the 1 step. The load instruction, on the other hand, has to do a computation, compute the address in memory that I need to go to, and then go to that address and get there, right? So that's these 2 stages in a load instruction. But as you can see, subtract again. So we're fetching now 2 instructions in every clock cycle instead of 1 instruction, okay? And so now we got 4 instructions completing in 6 clock cycles. If these were all 5-stage instructions, if we didn't have a superscalar, these are all 5-stage instructions, we fetch one at a time, how many clock cycles would it take to complete these 4 instructions? If we reach 5 and we fetch one at a time. Sorry? 20? I think that's too much. Right, if this one goes to 5, our second one gets fetched here, 1, 2, 3, 4, 5. Our third one, the subtract, gets fetched, I'm gonna draw it down here, 1, 2, 3, 4, 5. So that's 6, this is 7 now. This one gets fetched, is gonna get fetched here, right? So 4 plus 5 takes me, I must have screwed up, 4 plus 5 is 9, but it should end at 8. And this one would end up, it would be fetched there, right? We fetch, 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 fetch. Here's the first one. First fetch, second fetch, third fetch, fourth fetch. Yeah, I shouldn't have had that one. Okay, it's going to take 4, 5, 6, 7, 8, 9, right? So it's going to take 9 clock cycles to complete those 4 instructions, if they're all 5 stages and we fetch one at a time, versus here where we do it in 6 clock cycles, right? In a superscalar, because we can fetch 2 at a time. So the throughput increases by what? 33%, right? Which is pretty big. Okay, so that's scalar is, we're over time. We can finish talking about. And then here's my plan on Wednesday. I'm going to talk about the final exam, and I'm going to go over 2 or 3, depending on how much time we have. I'm going to review a couple of topics that people tend to find confusing. Cache. I'm going to look at pipelining again. What was the third one? Cache pipeline, data path. Okay? And hopefully work through a couple of examples of that to try and help with that. Okay? So we'll see you on Wednesday. Sorry for keeping you late. This